Okay, we're going to look at where this N sub I term comes from, which is the intrinsic carrier concentration. So to do that, I'm going to pull out a page from your textbook. And as you can see here, this is meant to be silicon. And these are silicon cores that are covalently bonded. This is meant to represent, shared electrons between the adjacent atoms. And this is a 2D representation. So, of course, silicon is 3D. And what this is showing here is that the valence band is full of electrons at 0K. There's a gap. And then you have the conduction band, which is essentially the high energy states that have split off, and they're like the anti-bonding orbitals. They're physically in the same location, but energetically at a much higher energy. So an electron could have one of these energy levels if it were free. So if it does break free from the valence band, it can go up here, and these levels are not to scale. They're actually much smaller. And once it's up here, it's free to run around. So when it does that, it leaves behind a empty electron seat here, which is called a hole. And okay, it looks like this. You have a bond, a covalent bond, and that covalent bond receives some kind of energy input and produces a free hole and a free electron. And these are mobile charges, and the free electron comes from the conduction band, and the free hole comes from the valence band. So when that bond breaks, it puts an electron up here and leaves behind this hole, both of which can move around. That's what the mobile means. Okay, so an equation we might write, you could see that this is a lot like something like, let's say, water dissociating to H plus and OH minus. And in chemistry, we write equations like this. We say that if, let's say, there's an equation that said A produces B plus C. That will give us an equation that looks like this. Well, the concentration of B times the concentration of C over the concentration A equals an equilibrium constant that follows an Arrhenius type relationship. Some constant K prime E to the minus Q over RT. So we know that this is a thermally activated, since it's a chemical reaction, it's thermally activated and related to temperature through this relationship here. Well, this is the same thing as this equation, thermally activated, and instead of writing the concentration of B and A, we would just write instead here the concentration of electrons and the concentration of holes over the concentration of bonds. Oftentimes, this concentration is considered so large compared to these that we just call this 1. So in this case, 2, usually called 1. And so what we have here is the number of intrinsic carriers times the number of intrinsic carriers, the product of this and this, N sub I squared is equal to K prime E to the negative Q over RT. Well, in our case, this is the activation energy barrier, and in our case, it's just the band gap. So what we have here is N sub I squared equals K prime E to the minus E gap over KT. K being Boltzmann's constant. This is different from this K, of course, which is a grouping of constant values. So let's go to the next slide. Whoa. Man, how'd that get there? So what we see here then is that the conductivity is Q times mu times N sub I, and that is Q mu K prime E to the minus E gap now over 2kt, because what I've done is taken the square root of this equation, n sub I squared equals k prime e to the minus E gap over kt. I've taken the square root of that to get this n sub I and put it into this term. Now, you can see I didn't change the k prime. This technically is a different k, maybe not k double prime. But this is equal to 1 over the conductivity. And we know that from our equation, R is rho times L over A. And if we flip all this upside down, we get this. A over L rho is 1 over R, which we know 1 over rho is the conductivity. So I can, again, substitute all these guys in here. And this term here becomes a grouping of constants. Then I take this whole thing, raise these guys to the -1 power, and I get this relationship. R is equal to A prime E to the plus E gap over 2k. Now this A prime I'm not really caring about. This is the grouping of the geometric terms and some of these other terms. But again, they're not a function of temperature, so I'm not worried too much about them. And I take the natural log of that, and I get natural log is equal to natural log A prime plus this term E gap over 2k times 1 over t. This is the equation of the line y equals mx plus b. And then if I plot that, I get the natural log of r, 1 over t. And using Excel, simply using the 4 data points that I gave you, you'll get a slope of around 3,360 and back compute in a band gap of roughly 0.7 electron volts from the data. I hope this helps.